Hello everyone, this is Huang. I'm a mechanical engineering with Pacific Northwest National Laboratory. Today I'm going to talk about reactive power modeling for building system to support building grid integration studies. This work is based on collaboration between the Pacific Northwest National Laboratory and the University of Colorado at Boulder. Yuan Liu, Jianmi Lian, Zhuogong Orbi are from the Pacific Northwest National Laboratory, and Yang Fu and Wang Dezhuo are from University of Colorado at Boulder. In this presentation, first I will talk about the motivation for our study, and then we will detail the coupling relationship between thermodynamics and electrical dynamics within building systems and how we capture them in system models. After that, we will present a case study to demonstrate the usage of the developed models. At the end, we will conclude our study and provide suggestions for future work. Let's start with motivation. It's becoming more and more clear that reliable operation of power grid requires reliability from demand side, especially buildings. As shown in the left figure is the famous dark curve. A dark curve describes the demand of power grid with a high penetration of photovoltaic power generations. So basically, the demand reaching the lowest value at the middle of the day, when the solar radiation reaching the peak value. In the afternoon, however, the demand rapidly increased when we're approaching the sunset. And then it's reaching the peak value in the late afternoon or early evening. After that, it was dropping significantly as the activity level of buildings or other demand resource drop dramatically in the late night. So those kind of shape of the demand is not really good for the supply side, because that means we have to really bring many generator online to providing power in a short period, but we only keep them running for a very short period, and then we have to bring them offline. And in the meanwhile, we know that the building power demand is kind of flexible, as shown in the right figure, by just adjusting the thermostat set point by either like a -2 Fahrenheit degree or like a +2 Fahrenheit degree, we can actually increase or decrease the whole building power by up to 10%. So that means, given that the building accounts for a significant portion of the power usage, it is possible to using the flexibility from the building side to really smoothing the demand curve, so that we can reduce the challenging in operating power grid. When enable the flexibility from the building side, one has to consider interaction between power grid and the building, because they kind of affect each other in an interactive manner. However, in the existing building model or power grid model, those interactions tend to be oversimplified. For example, we kind of assuming the supply voltage or frequency is constant for the building model. So those assumption or simplification may be justified for some case, but it may cause significant inaccuracy in building grid integration. To resolving this issue, we considered a modeling scope showing this diagram. From left to right, we have a transformer which is connected with a variable frequency driver, VFD. This VFD adjusting the supply frequency of electricity that's supplied to a motor. The motor then generates some mechanical work under induced magnetic field. The motor is then transferred the magnetic work to a motor-driven magnetic device, which interacts with the fluid loop to affecting the indoor thermal environments. Based on the different operation constraints, we may also have a feedback control loop to adjusting the input frequency of the VFD so that we have a closed loop interaction. We consider this system as an interface between buildings and the power grid system. And we think this kind of system is frequently observed in a typical heating, ventilation, and air conditioning system for commercial buildings. To model this interface system, we design different strategies for different components. For the VFD, we assume that its output frequency is equal to the input frequency signal. For the motor, we leverage an existing three-phase induction motor model from literature, and we implement that in Modelica. For the transition device, basically the shaft, we consider a first-order model showing this right equation group. Basically, we consider the induction between the magnetic torque and the mechanical torque. For the mechanical device, we leverage the existing flow mower module from the Modelica business library with a minor change in the interface. We would like to point out that using Modelica really simplifies the modeling process a lot. So Modelica allows us to directly specify equation rather than providing the solution to the equation, and also is making the connection of different components very easy. And in this figure, we're showing the a diagram of the top level figure of this interface system. So with the Modelica, we kind of develop a hierarchical structure of this model. So showing here is the top level, it's containing the major subsystems. One can see that this model has both the interface to the power grid and also the building system. It takes in the three-phase voltage and the frequency at the input and generating the real and reactive power that can be used as the input for the power grid models. And in MIUI, it also has the fluid port, which allow it to be kind of integrated into other system model or thermodynamic model directly. So after the development of the interface model is completed, we perform a empirical validation. So in this validation, we compare the real and reactive power calculation from this interface model against the same output from a commercial software. So for both to a simulation, we provide the same input regarding the input frequency, voltage, and also the mechanical load. And validation results showing that we can having a good matchless between the output from our model and then the output from the commercial software. After validation is performed, we also kind of conduct a case study. So in this case study, we consider a IEEE 30-node standard testing feeder system. So compared to the original test feeder system setup, we added two major assumptions. The first assumption is that we're assuming the supply voltage from the transmission system is constant. And secondly, we consider all the load that connected with this test feeder system are constant, except the one connected with the node 671. For the node 671, we assume it's connected with 10 identical 5-zone variable air volume system. So each system is controlled by ASHRAE guideline 636 control sequence, and you can find more detailed description of this system from the documentation of Modelica business library. We implement the model for this case study based on a co-simulation between GrabD and also Modelica. So GrabD is an open source modeling tool which used frequently to in the power grid domain to model the distribution system. of the power grid. And we basically utilize the interface model to build in the connection between the building system and then the power grid. We also leverage the FISO model from Modelica building library as the building system. And then because the building system are implemented in Modelica, so we utilize a code simulation engine called Phoenix, the framework for network code simulation, to connecting Gravity and then Modelica. So basically, we kind of converting like a Modelica model we create into a function Moncarve interface, and then we basically creating like a wrapper of this FMU with Modelica, which is a Python library for running function Moncarve interface. So with this kind of wrapper, we basically treated the wrapper as a federal of the Phoenix, so that we can realize the runtime conversion between Gravity and also Modelica. So in the case study, we consider two different scenarios. So scenario one is basically a baseline. So in this baseline, we kind of simplify the interaction between building and the power grid. So for the power grid, we're using the pre-generated load as input, and then for the building model, it's more like isolated mode. And for the scenario two, we basically consider those interaction with the interface model we created. For both two scenarios, we're using the Chicago weather file as a major input for the building simulation. So let's take a look at the result for scenario one. So for the each scenario, we're basically showing the two kind of information. So the first information is really the active and reactive power for this particular load connected with the node 671, and we're also showing the voltage for the adjacent node of this same like node 671. So for the power, we can see that in generally the shape of the like active power and the reactive power are kind of similar. So that means the power factor is basically almost constant across the day. And for the voltage, we can see that it's kind of having the similar shape as we saw from the the power profile. That means the power actually affecting the voltage distribution. And for scenario two, we're showing the same information, but we can see both the power result and also the voltage result are quite different from what we see from the scenario one. So basically, the first thing we can see that there is really a spike in at around 6 of the testing day. So the spike is caused by the transition of the system mode from unoccupied mode to occupied mode. So there is a peak power during the starting up of this fan during those transition period. And also we can see that when we kind of entering the occupied period, we can see the shape of the power, reactive power and active power are different. So that means the power factor is also kind of changing by time. And also we can see that when we entering the kind of steady mode, the changing of the voltage is relatively small compared with what we see from scenario one. That's because when we consider interaction between the power grid and the building, the inertia really smooths the rapid change of the voltage. So to conclude our study, first we propose a model can be used as the interface between power grid model and the building model. And also we perform a case study showing that having or have not considered those interaction between power grid and building may cause significant difference in terms of solution results. And for the future work, we would like to performing more validation when we have some real building data. And we also want to really use our model to as a virtual testbed to evaluate the different kind of demand side response strategy. That's all for my presentation. so much for your time and your patience, and I'm happy to take questions through email. Thank you so much again.